So here's the two assignments after the basic series. I thought it'd help guide some thoughts along how you would approach these if you haven't already, right? So we'll start with the first one. The first one I asked to write in terms of momentum, or the principle of conservation of momentum, what happened when the roll was thrown against the wall, right? So here we'll do the same thing. I'll use white color for my roll, right? What happened when the roll was thrown, as it went in there, its mass, it had a velocity, an initial velocity, right? And this is before it was thrown, u before. As it strikes against the wall, mass, and its final velocity, that very moment, and might as well not, I wouldn't even call it before, just say at that very instant of time, but for the sake of illustration, it's that, and we know this becomes 0. Now what happened to the wall? I'll use green, very massive, 10-inch concrete, very tough, into the ground, effectively an extension of the earth. It's not going anywhere. It obviously had an initial velocity before, was 0. What happened to that? Mass, its final velocity at that, let's say at that very instant, nothing happened, it stays at 0. Right? What happened to the collision, or just after that instant where they met, at that very, very tiny instant of time, we had m, initial, and I'll use after, minus, rapidly gaining velocity, quite literally, even if final velocity was very small, the fact that initial velocity would be 0, because at that instant of collision this was 0, because it had come into rest and then it came back out, mass times final velocity. And what happened here to the wall? Well, the wall didn't move. It was extremely, extremely massive. My cursive m is not getting me anywhere. I should have stayed with the, okay, its initial velocity after, also 0, it didn't move, minus its final velocity after, well, it didn't move at all. Now if I apply the conservation of momentum on every part of that system for the roll and for the wall, well, nothing happened to the wall really. So any change affected must have been affected on the roll. And if I, let's use another color, if I take that and say that these, now since nothing happened to the wall at all, there must have been something going on here. Very easily, if I equate the two, guess what happens? If I equate this difference and this difference, since mass really hasn't changed anywhere, I could simply write this as initial velocity before minus final velocity before, which is 0, would be equal to initial velocity after, which is 0, minus final velocity after. Now that is 0. That is 0. Guess what? Initial velocity before would be equal to, wow, this is interesting, a nice segue to the next section, which is basically velocity after being the same as velocity before, but the negative sign is an indication of an opposing direction. And we will do direction when we do the study on vectors and scalars in the intermediate section, but there you go, there you have it. Effectively, it's the same velocity. It literally came back into my hand. I didn't even have to move my hand closer. And that's what happened. So that's how you mathematically view what happened with the conservation of momentum. And nothing really happened here because velocity was zero in all these cases. The wall did not move because it was simply very, very massive. There was not enough strength in that motion, for lack of a better term, and we'll get to defining that when we go into intermediate and see what exactly that term for that strength will be, right? That's the answer to this one. Now, let's come in here. Let's take a look at this. So we have two objects, and let's use, since green, we'll put green away. Let's just use this. Let's say there's an object here. That's A. And here's an object at rest. We don't know its mass. Okay, and let's define A to be moving that way. We know that the mass of A, since we're using the colors, mass of A, we'll probably use a superscript for that. Mass of A, we know to be equal to 1 kilogram. We do not know the mass of B. We should try and find out. B is at rest. We can conveniently say the initial velocity of B is equal to 0 meters per second. Okay, we know that, use U, initial velocity of A is 100 meters per second. Now the question was, at what mass would A come to rest at collision? So if we were shooting A in a straight line to B, at what mass of M would A just come into rest? We know this wall is really massive. We saw what happened. We threw that and it came right back. The wall was at rest. It's very, very massive. It's literally connected to the earth. Almost infinite mass, you would say, relative to that tiny roll of tape. But the roll didn't come into rest. It came right back. Now we want to find out what would happen here. So let's see if we can extend the conservation of momentum to the point of collision. So at that very, so let's get really close. We've got object A here. And object B. So A and B. And it's that very, very tiny instant of collision. Right? So we want to bring A to rest. And for that particular system, A has lost all of its momentum. So we can just simply write this as the loss of momentum, or the change in momentum for A could be defined as its mass of A times its, maybe use the term UA, minus its mass times 0. Okay, that's A. Now what happened to B? If this is free floating, nothing's attached, there are there's no gravity, there's no air reaction, somehow the mass of A, mass of B times 0 minus whatever happened to be, the mass of B times its final velocity. This was at rest. Something happened to it. Now with the wall, obviously nothing happened. Its final velocity was 0, so everything got transferred here. You actually saw it rebound. But in this case, we know there is no rebound. Question states it comes into rest. It's like that roll would knock in, the roll would stay where it is, and the wall would move, right? In this case, it's just going to stay there. It's sort of like that box of coffee in that roll, right? What would happen? How would we, let's think about this. We just take this out as 0, and we write this simply as 1 kg times 100 meters per second. What would that get us? You know what, to simplify it, I'll go back to green now because I'm gonna write this equation in just one term. So I'll bring that 0 and that 0, so they're gone. I'll substitute them and say this would be 1 times 100, right? That's 1 kilogram, 100 meters per second. So don't forget kilogram, meters per second. And that should be equal to whatever is this mass that we need to find out times what the velocity of this would be right after collision. The question did not tell us what this velocity would be, therefore I would simply say the unknown mass of object B would simply be 100 divided by the velocity of B, whatever it moved with, right? Now, that's in meters per second. This is kilogram meters per second. So if meters per second cancelled out, I would simply write this as kilogram. And here's why I gave you this so you could think about it. If the wall didn't move at all, final velocity is 0. That mass approaches infinity. As I said, this is connected to the Earth. With respect to that roll, it's almost like infinite mass. But if that box of coffee actually moved a bit, rather slow, it actually had a mass. But this is how I want you to think about what happens in motion. And this is where you'll find, and this is probably some curricula, high school physics will give you problems like this. Two objects collide, what's the resulting momentum? Or they might ask you what kind of force was generated at the point of collision, or they might ask you to find, give you a velocity, ask you to find a mass. They might tell you that both objects had this is at rest, maybe it had a velocity. They might ask you to find out what happens. We also saw this one. I'll speak a lot more about direction. We'll get into problems like that when you get that negative sign and what direction means. But fundamentally, if you understand this idea, then you know what happened. Why did that wall move almost nearly infinite mass, right? Because you could also use this, bring it back here and say, well, velocity of that object B would be just 100 by mass. If that mass is nearly infinity, which is this wall since it's grounded into the Earth with a very big foundation and it's massive, the velocity is nearly 0. So the wall wouldn't move. So we've tied the two together. Hopefully you've thought about this, and if you hadn't, hopefully the explanation gives you the ideas behind it. But this is similar to problems you'll start encountering in most physics and mathematics curricula in high school, right? So we'll speak a little more about all the others as we go into intermediate. Thanks for staying on till then.